In this video, we are going to talk about polarity and solubility with a specific focus on organic compounds, which are just carbon-containing compounds, okay? And then we're going to use that knowledge to look at biological molecules, specifically the vitamins, in order to classify them, okay? All right, so let's recall what a polar bond is, right? So a polar bond is basically when you have an electronegativity difference between the two atoms that are bonded together in your covalent bond. So that covalent bond is polar when the atoms have different electronegativities. So let's look at the first example here. On the left-hand side, I have what we generally call a hydrocarbon. Okay, so this is a general term for any compound that contains only hydrogens and carbons, and that's where it gets the name hydrocarbon. So when you have hydrocarbons, you only have carbon-carbon and carbon-hydrogen bonds, which we know are nonpolar because the electronegativity difference between carbon and hydrogen is very, very small. So hydrocarbons will always be nonpolar because they do not have any polar bond. Polar bonds arise when you have atoms that have a very different electronegativity value relative to carbon. And these are going to be our heteroatoms with a focus on organic compounds. We're often going to see nitrogen, oxygen, and the halogens. So what this means is that since these heteroatoms have a higher electronegativity value, when they are bonded to carbon, they will often have, they will be a polar bond. So let's look at this first example here. We have oxygen. Oxygen is going to be slightly negative because it's more electronegative than carbon, which is slightly positive. That is going to make this bond here polar. Okay. And we're going to do the same thing with the other ones. Nitrogen is more electronegative than carbon. It's going to have that slight negative charge, and this is going to be a polar bond. Okay. If we look at the halogens, same idea, we will have a polar bond here. So anytime you see a heteroatom in an organic compound, that bond between that heteroatom and carbon will be a polar bond. Okay. So that is how we classify bonds. Now, we need to use that information to determine whether a molecule will be polar as a whole. So just because a molecule has a polar bond doesn't necessarily mean the entire molecule will be polar. So there are two things that we need to consider for that. Recall that we're going to have to compare how many polar bonds we have versus nonpolar bonds, since they will be competing for whether a molecule will be overall polar or overall nonpolar. And then we will also need to consider the shape. So let's look at comparing first just the amount of polar versus nonpolar bonds. So in my first example, again, I have ethane, which is just a hydrocarbon. There are no polar bonds here because there are no heteroatoms. It's just carbons and hydrogens. So that's going to be a nonpolar molecule. So that will be straightforward. Then we have chloroethane. In this example, we have two carbons here, and then we have that chlorine, that this bond between the carbon and the chlorine will be a polar bond. So since you have that one polar bond and your molecule is small, meaning that the nonpolar region, which is everything over here, all of this, since this nonpolar region is small, that means that having just one polar bond will be sufficient to make this entire molecule polar. That's in contrast with what we have here with butanol. Okay, with butanol, we have this oxygen here. Yes, we have some bond dipoles like this. Okay, so this part of your molecule is polar, but look at how long this carbon-hydrogen region is. And these carbon-hydrogen bonds are going to be nonpolar. So once you get up to 4 carbon hydrogens, as you see here in butanol, even though you do have a polar bond, your molecule will behave more as a nonpolar molecule. So yes, butanol will be slightly soluble in water, okay, but not by a lot, not as much as chloroethane, for example. And so we say that butanol is a nonpolar molecule because it will behave generally more like a nonpolar molecule. All right, so we have to consider how many polar bonds versus nonpolar bonds to classify a molecule as polar or nonpolar. But we also need to consider the shape. So here I have an example, the dichloroacetylene, where you have a lot of polar bonds, right? Most of your molecule is polar bonds. This carbon-chlorine bond here is polar, and so is the other one. Both of these are polar. The only nonpolar bond we have is this carbon-carbon bond here, triple bond. Okay. But because these polar bonds are pulling in equal and opposite directions, meaning the bond dipoles are in opposite and equal directions, they will actually cancel out. And so because the shape of my molecule is linear, That is why these bond dipoles cancel, because it is linear. So when we consider the shape, we recognize that even though I have polar bonds in this molecule, my molecule shape will make it nonpolar. Let's consider a scenario where you do have polar bonds, but the shape allows you to have a polar molecule as well. So here I have two polar bonds. This is going to be a similar situation as we saw with chloroethane, where with methanol, we have these bond dipoles, where they, because of the shape of the molecule, these bond dipoles will not cancel out, and therefore you're going to have what we call a net dipole. So that means that this molecule overall will be polar, not just because the bond dipoles don't cancel, that's necessary, but also because we have a very small nonpolar region here. Okay? So those two things together will make methanol a polar molecule. All right, so now that we have reviewed how it is that we determine how when a molecule will be polar, let's review our rules of solubility. Again, we're going to touch on some things we've already talked about, and then we're going to add a little focus to just organic compounds. Okay, so the rule of solubility of like dissolves like will still apply. We're just going to add a small nuance. Okay, so let's recall what we've already learned. So when we were trying to determine whether a compound will be water soluble, we basically had to determine whether the solute is nonpolar or polar. So if water is going to be our solvent, water is a polar molecule. So this means that if like dissolves like, then if you have a nonpolar molecule, it will not dissolve in water. And if you have a polar molecule, it will dissolve in water. So that's where our ability to be able to determine how many polar bonds we have, then determine whether the shape of the molecule will cancel the bond dipoles. Okay? That will allow us to determine whether a molecule is polar or not. And then we can determine whether it will be soluble in water. So again, hydrocarbons, which contain only carbons and hydrogens, that's an easy classification, it's nonpolar. Then other nonpolar organic compounds, all of those will be insoluble. For polar molecules, we have to consider whether they contain enough polar bonds to basically outcompete the amount of nonpolar bonds. And then we need to determine whether those polar bonds, if they are present, if they will cancel. All right, so that is how we can determine if something will be soluble in water. But now let's add a small nuance where we're now going to talk about organic solvents. So previously we were very concerned about whether something will be soluble in water or not. Now we're thinking about whether things are going to be soluble in organic solvents. What's an organic solvent? It's just a solvent that contains a compound that has carbons. So this is a carbon. Again, remember that organic just means carbon containing. So this is a carbon containing compound that will serve as your solvent. So we no longer have water as a solvent here. And the general rule here is that most, not all, but most organic compounds will be soluble in organic solvents. So what this means is that you will have situations where even if your organic compound is polar, you can still have it be soluble in an organic solvent that is non-polar. So the like dissolves like rule here still applies in that an organic compound is soluble in an organic solvent. Okay, so let's look at an example of how we would apply all of this into classifying or predicting whether something will be soluble in an organic solvent or in water. Okay, so let's look at what we mean by organic solvent. Again, here, this is just an example. This is diethyl ether. It's just an example of a common organic solvent. This is the skeletal structure. Okay, but here in this table, we're talking about just any general organic solvent. All right, so let's look at hexane. The first thing we notice about hexane is that it is a hydrocarbon. So immediately, we know that it's going to be nonpolar. It only has carbon-carbon and carbon-hydrogen bonds. So what this means is that first, it is an organic compound. So organic compounds will be soluble in organic solvents. So immediately, we can say this is going to be soluble. I'm going to write S for soluble. However, because it's a nonpolar compound, this is where I need to determine, or this is what I will use to determine whether it will be soluble in water or not. So since it is nonpolar and water is a polar solvent, these will not mix together. It will not be soluble. So I'm going to write an I for insoluble. So hydrocarbons, because they're nonpolar, are insoluble in water. Now let's look at ethanol. Ethanol is going to be a polar molecule because we have bond dipoles here. And then the region that is non-polar, which are these carbon-hydrogen bonds, is very small, okay, relative to the amount of polar bonds that I have. So because of this, this molecule overall will be polar. Now, if it's polar, we immediately know it is soluble in water. But because it's an organic compound, meaning it's a carbon-containing compound, it will also be soluble in most organic solvents. Okay? So this is an example where you have a molecule that is soluble in both organic solvents and in water. Okay, lastly, let's look at cholesterol. Here we see that we have a hydroxyl functional group right here, OH. This is going to be a polar, this is going to have a polar bond in this direction. But we then see that the nonpolar region is very large. So this is a large nonpolar. So because it has such a large nonpolar region, even though this molecule has one polar bond, it will generally behave, it will behave overall as a nonpolar molecule, meaning it will not be able to dissolve in water or become soluble in water. So because of that large nonpolar region, it's going to be insoluble. But it is an organic compound, therefore it will be soluble in an organic solvent. So diethyl ether here is a slightly, so the organic solvent that I've put here as an example, it is slightly polar, but the point here is that when you have an organic solvent, most organic compounds will be soluble, independent of whether they're ethanol, meaning they're polar, or they're cholesterol, meaning they're nonpolar. Whether they're polar or nonpolar is going to make a very big difference in whether they are soluble in water. Okay, and meaning a polar molecule will be soluble in water, when a nonpolar molecule will not be soluble. Okay. So another way to think about this, I want to start thinking about these phenomenon in terms of intermolecular forces that we've already talked about. One way that you can talk about the forces in cholesterol is that the London dispersion forces outweigh the dipole-dipole and hydrogen bonding interactions. So London dispersion forces, recall that these are the only forces present in nonpolar molecules, okay? Because there are no other intermolecular forces present there, since they cannot have dipole-dipole or hydrogen bonding if there are no heteroatoms, okay? So the only forces that are present in this region of the molecule are going to be the London dispersion forces. And so we can talk about this by saying that the London dispersion forces are outweighing the dipole-dipole, which would be the forces present here, right? Dipole-dipole, because there's a polar bond there, and hydrogen bonding. This hydrogen can hydrogen bond because it is bonded to oxygen, so that will allow it to hydrogen bond. So even though it can hydrogen bond and it has dipole-dipole interactions, because those are outweighed by the London dispersion forces present in the nonpolar region of the molecule, overall, this molecule will be nonpolar. All right. So now with all of that knowledge, let's start applying to be able to predict whether a molecule will be soluble in water. Okay, and then we're also going to take this opportunity to start identifying functional groups to practice being able to identify these. Okay, so we're looking here at balsamic vinegar and olive oil. So acetic acid is going to be the component in balsamic vinegar that gives it its odor and its flavor. And then oleic acid is going to be a fatty acid. It's a fat. So it's a fatty acid. We're going to learn about fatty acids later on in the semester. But this is going to be a fat. So let's look at its structures. Let's first identify the functional groups. Okay, so let's start with acetic acid. Immediately I see that I have a functional group right here. So recall that the black spheres are going to be your carbons, the red spheres are oxygen, and the white spheres are hydrogen. So in this group right here, what I have is a carbon double bonded to an oxygen. That same carbon is then bonded to another oxygen, which is bonded to a hydrogen. So I'm going to go ahead and write it up here. So I have carbon. And this type of bonding pattern is exactly what a carboxylic acid functional group is. So this is a carboxylic acid. And to this carboxylic acid functional group, in acetic acid specifically, we have a methyl group or a CH3 group attached to it. Okay, this is what's attached to the carboxylic acid functional group. If we look at oleic acid, we'll see that it also has a carboxylic acid group, and it's right over here, where we have a carbon double bonded to an oxygen. That same carbon is then bonded to an oxygen, and this oxygen bonded to a hydrogen. So you have to have all of these features in order for it to be a carboxylic acid. And then what we'll see is that for oleic acid, we have a very long chain of carbons and hydrogens right here. Okay. And all these carbons and hydrogens, it's basically a long hydrocarbon chain. These are going to have a nonpolar character. But the carboxylic acid, because it has those heteroatoms, this is going to be a polar group. So these two are polar. This will be nonpolar. So now let's compare the two. So acetic acid has a polar group, and then it has a very small nonpolar group. So overall, our acetic acid is going to be a polar molecule. This means it will be soluble in water. Now let's look at oleic acid, which we can find in olive oil. Okay, it does have a polar group, but it has a very large nonpolar group. So this means that fats are going to be nonpolar, and therefore, this is why they are not soluble in water. So this is how we can start identifying functional groups, recognizing that many functional groups are going to be polar groups, but we also then need to consider the rest of the molecule. How much nonpolar character do I have in the rest of the molecule? And if it's a lot of nonpolar character, then your molecule will behave overall as nonpolar. So now let's put all of that together to start looking at some structures of vitamins and be able to predict whether they're going to be water soluble or this term called fat soluble. So vitamins are going to be organic compounds, and we need them in very small amounts for normal cell function. The interesting thing about vitamins is that we cannot synthesize them. That means that we have to obtain them in the diet. So with vitamins, we classify them based on their solubility. Okay? So there are two classifications. There's the fat-soluble, and there's the water-soluble. So the fat-soluble vitamins is defined as vitamins that can dissolve in an organic solvent, but is insoluble in water. So really what they're saying here, recall that a fat, this is oleic acid, this is the same molecule we just looked at in the previous slide. Fats are going to be nonpolar molecules. So when we say that something is fat soluble, we're basically saying that they are soluble in a nonpolar solvent. Okay, so nonpolar, so fat soluble means soluble in a nonpolar solvent. Okay, so if something is going to be fat soluble, it has to be nonpolar. If something is going to be water soluble, then it just has to be polar, and that is characterized by having many polar functional groups. Okay. For fat soluble proteins, that will be characterized as having very few polar functional groups, but many carbon-carbon and carbon-hydrogen groups. So let's look at several vitamins. Okay, here we need to determine whether vitamin A is going to be fat soluble or water soluble. So vitamin A is going to be a very important vitamin for vision. And it also helps with mucous membranes and the skin. So it is a very important vitamin. So let's classify it. First thing you want to do is go ahead and locate your functional groups. I see that I have a hydroxyl group here. This is called hydroxyl. It's basically just an OH group. And we know that this oxygen is going to have polar bonds in this direction. Okay, so it is a polar group. But I'm also going to recognize that there is a large region that is just carbon-carbon and carbon-hydrogen. It's a large nonpolar region. We can call this nonpolar. We will also sometimes use the term hydrophobic. Phobic means fearing, hydro means water. So if it's water fearing, it means it does not like to mix with water. Therefore, it must be nonpolar. So we can say that vitamin A has a large hydrophobic region. So for this reason, it will behave overall as a nonpolar molecule. So if it's nonpolar, then this means that it must be water soluble. Fat soluble. So vitamin A, because it has many nonpolar carbon-carbon and carbon-hydrogen bonds, and it only has one OH group, it's not enough to outweigh the dispersion forces of that hydrophobic tail. This is going to make it fat soluble. Let's look at another example. Now we have vitamin C. First, locate all the functional groups. Right? These functional groups are going to be polar because they contain heteroatoms. So I have 1, 2, 3, 4 hydroxyl groups. And then I see I have another functional group here This functional group is a carbon double bonded to an oxygen, which is bonded to another oxygen. And then these are bonded to some other carbons. I'm going to use the letter R just to say that it is some carbon entity. It doesn't matter what it is as long as it's just carbon. And then this will be bonded to some other carbon. I'm going to say R prime just to show that it's some other carbon containing group. But my focus here is that I have a carbon double bonded to an oxygen, and then that same carbon is bonded to another oxygen. This is going to be the ester functional group. Okay. So what I recognize in my vitamin C molecule is that I have a lot of polar groups, and I have very few non-polar character here, the carbon-carbon and carbon-hydrogen bonds. So what this means is that vitamin C is most likely going to be a water-soluble molecule, vitamin, and it is because of those characteristics. So vitamin C is very important for collagen and for connective tissue of the skin, and it is known for being responsible for scurvy, which is a very serious condition where you have issues with bleeding and bruising and wound healing, which was very prominent back in the 1600s. Okay, so this is a very important vitamin, and it is going to be a water-soluble vitamin. All right, let's do two more. Here we have vitamin B3 and vitamin K1. So with vitamin B3, again, identify your functional groups. I have one here. This is going to be a carboxylic acid. And then there's another one right here. This is going to be a nitrogen bonded to other carbons. This is called an amine group. All right, so I have two polar groups here, and I have some non-polar character for sure, all of the other carbon-hydrogen bonds. But this is going to be few enough non-polar bonds to give me a polar molecule. So here I have two polar groups. The non-polar character is not that large, and so this is going to be polar. What this means is that this is going to be a water-soluble vitamin. Let's contrast that with vitamin K1. Immediately, I can already see I have a very long hydrophobic tail here. But let's go ahead and look at our functional groups. Always locate those. Okay, I see I have a carbon double bonded to an oxygen here, and I see this here. When you have a carbon double bonded to an oxygen, and then that carbon is bonded to some other carbons, doesn't matter what they are, this is called a ketone. So I have ketones here. These do contribute polar character, ketone. But because I have such a large non-polar tail here, such a large part of my molecule is non-polar, that will make this molecule non-polar. And because of that, it's therefore going to be fat-soluble. Okay. So that is how you can classify whether something will be water-soluble or fat-soluble, specifically looking at vitamins. So why do we care about this? Why do we classify vitamins this way? Well, it turns out that vitamin solubility is what determines how they are stored in our bodies. So if we can understand or be able to predict whether a vitamin or a compound will be fat soluble or water soluble, that will let us know how it's going to interact with our bodies. So here, vitamin A and other fat soluble vitamins, those are going to be stored in your liver. Because the water soluble vitamins, those are excreted in the urine. Why are they excreted in the urine? Well, the urine is going to be a polar solvent because it's mostly water. So what that means is that the water-soluble vitamins will be able to dissolve in the urine, and that's why they're excreted. So if you consume more water-soluble vitamins than you need, those will just be excreted in the urine. That's in contrast with fat-soluble vitamins, where they're not going to be excreted in the urine. They do get stored. So with fat-soluble vitamins, sometimes we need to be careful about how much we consume, because if we overconsume, they do get stored in our liver. And sometimes overconsumption or that storage in our livers can cause some health problems. Basically, that's what it means to reach a toxic dose. So with fat-soluble vitamins, there is such thing as a toxic dose, something we do need to think about and consider, because it can cause some health problems because you don't excrete them. But with water-soluble vitamins, that's not much of a concern because they just get excreted in the urine. So this is an example of why it is important to be able to determine solubility and why we classify vitamins in this way, because it tells us a lot about their functions.